so we're going to be looking at the shapes of molecules, what they are, and how they can have an effect on the molecule. So our shapes of molecules are going to be determined by the number of bonds to a central atom in that molecule, and also the number of lone pairs of electrons surrounding that central atom. Now, lone pairs are electrons that are not bonded. So they're just hanging out, and it's just the ones on the central atom. The lone pairs around the outside atoms don't matter. They don't have an effect on the shape of the molecule. But the lone pairs, the unbonded electrons on the central atom, do have an effect on the shapes of the molecules. And so what you would do is you would draw the Lewis structure to determine how many bonds and how many lone pairs you have on a central atom, and that's how you determine what shape you're going to have. Now, if you don't draw the Lewis structure, another way that you can determine the shape is by building the actual molecule using those model kits that we've used. So you can actually build it as well, and that will also help you determine what the shape is if you don't draw the Lewis structure. So either one, you can still figure out what the shape is. Then the first basic shape that we have is linear, and linear can be in two different molecules. So either the molecules that have just two atoms bonded together. So our examples here, we have hydrochloric acid, HCl, and we've got carbon monoxide, CO. So in both of those cases, it would just be two atoms that are bonded together. And so the only shape they can form is a linear shape. Another way that you can get a linear shape is when you have three atoms bonded together, and the central atom has all bonded valence electrons. So there are no lone pairs, no unbonded electrons on that central atom. Remember, the outside atoms don't matter, but the central atom does. So let's look at some examples of those. So we have carbon dioxide, CO2, and carbon disulfide, CS2. Those would be two examples in which you'd have all bonded valence electrons. So how that would work, or what it would actually look like, let's take this one out of here, is with two atoms. So this could be an example of HCl. It's just a line, linear shape here. You can see, it doesn't matter which way you turn it. I turn it in any direction, and it's still a line. And that's just with two atoms. You can even have it where it's double bonded. So this would be another example of two atoms, and the only shape it can be is in a line, even if there's a double bond, or even a triple bond. So this is the carbon monoxide one, CO, and as you can see, that's a triple bond on there. It's still a line. So it doesn't necessarily matter how many bonds you have. There really is no central atom when there's only two atoms, so that part doesn't really matter in this case. You just have two atoms. That's the only choice it can be, is that linear shape. Then another way that we said we could have a linear shape is if you have three atoms bonded together and there are no lone pairs on that central atom. So the purple atom in here is the central atom. So one of the ways that you would have no lone pairs on this, and it would still be in a linear shape, as you can see, even though I kind of move it around, it just adjusts as I move it, but it's still in a line, is when you have a triple bond here and a single bond there. You're going to always have four bonds to that central atom. So this is one way, three bonds on one side, one bond on the other side. It doesn't matter what side is which, still in a line. Then another way that you can have a linear with three atoms is to have it double bonded. So you have four bonds to that central atom here. So there are no lone pairs, there are no unbonded electrons on that central atom because it has four bonds. Each bond has two electrons in it, and therefore it would have 8 valence electrons, and that's what most atoms want to have. And so that makes them stable, just like the noble gases. So by having 4 bonds to that central atom, there are no lone pairs on it, so therefore it would be a linear shape. Then we have a bent shape. So this is another basic shape that we'll be using in class. So it's kind of a V shape to it, in which you have 3 atoms bonded together, But the difference here, because linear can also have 3 atoms bonded together, but the difference is that the central atom has at least a lone pair of valence electrons, and then it would have the 2 bonds. So water is a V shape to it. It's not a linear molecule. And then SCl2, so sulfur dichloride. So looking at some examples of a bent shape, we have the 2 bonds right there, and once we add that lone pair of electrons, see how these electrons are kind of hanging out? They're all alone, they just hang out together. Those lone pair of electrons push those bonds together, and so therefore it's got a bent shape. You can't straighten it out. Okay, so it's just it's got a bent shape to it, and if you look at it like kind of like the V shape to the molecule, because you wouldn't see these lone pairs on that. That's just for our visual here. You would just have, here would be your oxygen and your 2 hydrogen. So that would be the shape of a water molecule, for example. So by having 2 bonds, so here's 1 bond, here's the other bond, and then here's your lone pair of electrons, or we could add another lone pair of electrons. So it would still have that bent shape to it. No matter what way you turn it, still has kind of like V shape with those lone pairs on there. So you've got 2 bonds and 1 lone pair, 2 lone pairs, doesn't really matter. It's still going to make that bent shape. 3 atoms and lone pairs on that central atom causes it to have a bent shape. Then another one that we have is trigonal-pyramidal, and this is kind of a pyramid-ish kind of a shape. And you have 4 atoms bonded together, and that central atom is going to have 3 bonds and then 1 lone pair. So NH3 is an example of this, and PCl3 is an example. So looking at what you would have here, you'd have, so we need another bond on here, and then you'd have a lone pair. And this would cause it to have that slight pyramid kind of shape. Move it around a little bit. So kind of has a slight pyramid shape to it. So this one is trigonal-pyramidal. So I have 4 atoms, 1, 2, 3, 4, and then on that central atom there is a lone pair, and so that's why this isn't flat. This is slightly raised, so it does have that slight pyramid kind of a shape to it. Then our last one that we're going to be looking at is tetrahedral, and tetrahedral is also kind of pyramid shaped. It's just a little bit maybe better identified pyramid, but still kind of pyramid shaped. You have 5 atoms bonded together, and that central atom is going to have 4 bonds to it and no lone pairs. So methane, CH4 or CF4, carbon tetrafluoride, that also would have a tetrahedral shape to it. So back to that. Right. Okay. So let's add 4 bonds there. So we have 5 atoms on here. And if we kind of move it around a little bit, you can kind of see how it would have a little bit more of a pyramid kind of shape to it. And that is our tetrahedral shape. So no lone pairs on here because we do have the 4 bonds. So we have 8 valence electrons. We're all good to go. No lone pairs on that central atom. Does not matter if there's lone pairs on any of these outside atoms. That's not going to affect this shape at all. And you can see that you'd have a tetrahedral shape. So then the goal for you is to figure out how many atoms are involved, because if you only have 2 atoms, it can only be linear. If you have 5 atoms, like in this example, it's going to be tetrahedral. If you have 4 atoms, it's going to be trigonal-pyramidal. The only one that you really have to think about is the 3 atom ones. So is it going to be bent or linear? And that just depends on the lone pairs. So otherwise, every other one, just count the atoms and you can identify the shape of it. Then why would we care? Like, why is it important? Well, because it's going to help you determine if a molecule is polar or nonpolar. Now remember, a molecule is different than a bond. A bond's polarity is just determined by the electronegativity difference. So if your electronegativity, so you just look at each atom, and if your electronegativity is lower than 0.4, then you know that's going to be a nonpolar bond. If it's higher than that, then it's going to be a polar bond. And then even if it's higher than that, then it'll be an ionic bond. But bonds are different than molecules. So you can have polar bonds, but have it be a nonpolar molecule because of its shape. So in order for it to be a polar molecule, you must have two poles. So when you think of two poles, you think of North Pole, South Pole, right? Or on a magnet. Well, for molecules, we're looking at a positive and a negative side to the molecule. So the shape has to come into effect here to figure out, do you actually have a positive side and a negative side, or do you have two negative sides? If you have two negative sides, that would make it nonpolar, because a nonpolar one means there's no positive and negative side. So there could be two negative sides, there would be two positive sides, maybe there's no positive or negative. So you have to make sure the shape is taken into account whenever you're trying to figure out if the molecule is polar or nonpolar. When you're just looking at the bond, you simply look at the electronegativities and find the differences between. But when you're looking at the molecule, you have to take the shape into account and figure out, well, what are each of the bonds? And then are they polar? If they are, then you identify the positive and negative atoms. And then from there, you figure out, okay, looking at my molecule, is my molecule a polar molecule? So you have to have a positive side and a negative side. So top positive, bottom negative, or left positive, right negative, or something like that. If you have top positive and bottom positive, well, then that's not a polar molecule. If you have a negative left and a negative right, that's not a polar molecule. It has to have one side positive, one side negative. That one, and we're going to take a quiz. So let's look at CF4. What shape would this be? Well, there's only one choice for 5 atoms in our class, so that is going to be tetrahedral, because a linear would be for 2 atoms or 3 atoms if there's no lone pairs on that central atom. Bent would be for 3 atoms if there were lone pairs on the central atom, and trigonal pyramidal is for 4 atoms. So CF4 has 5 atoms, so therefore it's tetrahedral. Then SiO2 has what shape? So you'd want to either build this with the molecule set or draw out the Lewis structure. And once you do that, you will determine that there are no lone pairs on the Si. So the Si goes in the center. There are no lone pairs on that Si, and therefore it would be bent. Sorry, it would be linear. So that one would be linear because there would be no lone pairs on the Si. So SiO2 is linear, 3 atoms, no lone pairs on the central atom. So you do that by either building it or by writing the Lewis structure for it. Then we have PBr3. So we want to know, is this polar, nonpolar, or ionic? So we're going to bring up our electronegativity chart. And we look at phosphorus, which is 2.19. Now your chart might be slightly different, which is fine. We're still looking at the differences here. So 2.19, and bromine is 2.96. So either way, the difference between them is greater than 0.4. So we would know that this would be a polar bond between each phosphorus and bromine. And there would also be a lone pair on the central atom of this one. And it's going to have a trigonal pyramidal shape. And whenever it has a trigonal pyramidal shape, that means it is a polar molecule. So polar bonds, trigonal pyramidal shape, you're going to have a polar molecule. Then the negative side on IF would be, well, all we have to do is look at the electronegativity of iodine and fluorine. And we know fluorine is always going to have polar bonds unless if it's bonded with itself. That's the only way that fluorine would not be involved in a polar bond. So in this case, fluorine 3.98, iodine 2.6, 6,6. So fluorine has a higher electronegativity, so therefore that's going to be the negative side. So this would be a polar molecule, because you would have iodine, because it's only two, remember it's only two atoms, so it's going to be linear. So iodine, if that one's on the left, fluorine is on the right. Fluorine would be the negative side, iodine would be the positive side, because iodine has the lower electronegativity. So this would be polar, because you'd have not only a polar bond in there, but this would also be a polar molecule, because iodine would be the positive part and fluorine would be the negative part, based on the electronegativities that we have right here. Then our shape of a molecule depends on your favorite, right? To call it apply. So it's going to be all about the central atom. So lone pairs on the central atom would be correct, and the number of bonds on the central atom would also be correct. We don't care at all about the lone pairs on the outside atoms or the number of bonds on the outside atoms. We only care about those central atoms. So that's how you're going to determine the shape. And then that shape, once again, can help you figure out the polarity of the entire molecule. Because even though you have polar bonds, you may have a non-polar molecule. So we always have to take the shape into account.